Magnetic resonance imaging, commonly known as MRI, is one of the most powerful tools doctors have at their disposal to diagnose all sorts of ailments and make treatment plans to heal those which are sick. MRI scanners employ powerful magnets which produce a strong field which forces protons in the body to align. The protons are then stimulated and sensors in the MRI machine are able to detect the energy release as protons realign with the magnetic field. The time it takes to realign and the amount of energy released changes based on the properties of the molecules. As expected, a large amount of data is generated by these sensors. This data needs to be parsed, analyzed, and rendered in order to be in a useful format for the doctors and radiologists to look at. This is where software comes into play. In our project, we worked with the Boston Children's Hospital in the Fetal Neonatal Neuroimaging and Developmental Science Center in helping them deploy CRIS, the Children's Research Integration System. What exactly is CRIS? How does it work? And where do we fit in? CRIS, for those unfamiliar with the technical workings of the system, is a cloud radiology platform used by clinicians and researchers at the Children's Hospital in Boston. It allows users to upload scans into a private cloud at CHB and perform post-processing functions on medical scans such as MRI and CT. These functions reside in plugins which reside on the cluster. This creates severe limitations for expanding CRIS onto other clusters. CRIS does not assume users have any knowledge of the command line or other computer skills other than drag and drop file management. CRIS consists of a web front-end which interacts with a back-end. This back-end controls the database, file system, DICOM listener, and the cluster. This presents a simple interface for end users. It allows for easy file uploading, clear file output, and a browser-based viewer. It is also quite scalable and extensible. It can support many users, and plugins can be added at will without damaging current functionality. Our counterpart team last year designed and built a Python-based scheduler to allow CRIS to work on the Massachusetts Open Cloud. However, it was noticed that the standalone Python applications would run into problems with dependencies, and as such, our group set about on the task of Dockerizing these plugins and doing a proof of concept project to show that it would be feasible to have Docker applications running within the CRIS system and executing tasks. What we want to do is to add Docker functionality to CRIS. Docker is a container framework which automates deployment of software by providing operating system level virtualization. It puts everything your app needs into a container. You can choose the operating system, the binaries, the plugins, pretty much anything you'd like. It also works on the write once, run anywhere model, which would allow easy deployment of CRIS across multiple clusters. We wanted to create an infrastructure based on the existing installation of CRIS, which can transfer imaging data to Docker plugins and schedule jobs as needed. We wanted to arrange existing plugins into this system, which would isolate plugin dependencies from the underlying cluster on which they are executed. This would allow for future revisions on plugins without affecting the overall system. We also wanted to ensure that CRIS could be run on other cloud systems outside of the Children's Hospital, such as Amazon Web Services or the Massachusetts Open Cloud. Initially, we ran into a few issues with getting the base CRIS image to work on the Massachusetts Open Cloud. Certain aspects of the architecture were changed from last year, which made the process substantially more difficult and involved. Eventually, however, we were able to get CRIS up and running on the cloud server without an issue. The question then came of how these plugins worked. because without a good understanding of the functionality of the plugins, it would have been impossible to Dockerize them. The plugins are written in Python and contain functionality for file input, file output, and performing the necessary operations on these files. What we want to do is create a container with the ability to pipe files between itself and the CRIS file system. This could be done by binding Docker containers to CRIS via TCP connections. Once the image files are inside the container, the programs are executed to transform the data. Docker images are created by writing a comprehensive Docker file, a set of instructions which specify the base image, declare environment variables, libraries, dependencies, and the plugin itself. Essentially, a Docker can build images automatically by reading instructions from this Docker file. These are the commands specified above, and they are ordered sequentially, and they are needed to build a given image.
To review our user stories, we have 3 principal individuals who might be using CRIS. Now, all of them would, in this case, be affiliated with Children's and involved in research or potentially clinical uses to varying degrees. You have folks who may be viewing MRIs but are really not expert in their use. For them, CRIS provides convenience more than anything else. You don't need a powerful machine to be able to do some very, very basic image processing. Radiologists and other specialists who use MRIs on a more frequent basis may have slightly more complex needs, but fundamentally, CRIS helps them out by, again, allowing them to run analyses and share files without necessarily needing to have a powerful machine in their use. And much of the same goes for researchers. For researchers, CRIS provides some additional benefits in that being able to load scripts for FreeSurfer, one of the main utilities used, and many of the other plugins, allows them not to have to deal with a lot of command line. And in particular, with working with these programs, the command line can get very, very messy very quickly. To have a nice overview of what the system is, let's walk through how it works. So again, as mentioned, the front end of CRIS is a series of Python plugins which allow users to enter files through a web interface that isolates a lot of the command line arguments. So one of the first items we implemented was MRI info. It's a step up from Hello World, but it actually uses our Dockerized FreeSurfer utility. So we'll grab an existing MRI file. Give it a sec. We'll see that it's been added to the feed. It's created a running directory both with output and potentially standard error output, but also it's created a copy of the original file. Finally, we've been able to cat the information from MRI info into a nice readable file that we can also save and move around just as easily as we did our MRI file. So let's pull back the curtain a little bit further and actually just show how this all comes together. So let's head over to the actual hosted site here. We'll go through the architecture that we've set up in tandem. So together this implementation is relatively lightweight. It builds upon the existing CRIS architecture. Now there are 2 ways that if you were to build this system yourself, you could establish it. You could use the original CRIS Reloaded, which can be found on their site, or you could potentially get the CRIS Portable virtual disk image that we built this from. They're very similar and should have similar functionality. So going into the plugins themselves, we'll check out that same item here, MRI info. So apart from our little splash screen here, what we really have is we start out, we use the add parameter function, which is a very nice feature of the plugin architecture. If you create parameters, it will automatically parse arguments and get appropriate inputs with alt text and more information. And what's really going on is that as this runs, it's calling crun, which is a bunch of shell script functor commands, and ultimately we are just calling a set of paths to our Docker file and a script that automates that, and quite literally we are catting out to our output file. While grabbing some text info from an MRI file is all well and good, the real money is in actually doing image conversion, which is the reason why you need a cluster to begin with for a lot of this stuff. So we'll move on to our Dockerized MRI convert utility. Again, we'll grab an MRI that we have handy here. And here we can actually just pick a format. I'm going to use MGZ and let her rip. So and again, as is standard practice within the plugin architecture here, this is automatically generated by the crun functors, but here, again, we're saving copies of our input file and output file. As you can see, we'll give it a sec to load. We have our original input file here in the NII format, or NI if you're partial. And then now we've got the MGZ format converted pretty seamlessly. Now, that having been said, merely converting files is good, but a lot of what users want to be able to do is to modify those files as well. Thankfully, we don't even have to leave the MRI convert utility to start taking advantage of the Dockerized version. Here, we're just going to change things around just a little bit. Start a new job. And so again, we have our starting MRI. Now to walk through this from the bottom of somebody's head all the way to the top. Again, just remember that orientation. Bottom is to the left, top is to the right. But in our output file here, top is to the left, and bottom is down to the right. One of the interesting things about working with Chris is that it blends both the Python front end with the command line back end is that if you're not careful, or if you have a user who's a little curious, there is quite a lot that you can find. I may not be a major hacker, but there might be some evil that somebody could do with this. With the file browser, allowing us some relatively inside information about the workings of the system, having potentially unsanitized shell input creates a whole lot of problems. Now, it's not simply as easy as doing something like this, but one of the objections is that you do have to at least be able to log into the system and know what you're going to damage. But part of the issue is that this code is available publicly online. And it's usually a safe assumption that if people can see your code, they're going to be, by definition, looking for holes in it. Now, as it happens, you don't even have to necessarily be able to get access to the system directly. Emails are easy to spoof, and it's not hard to imagine somebody who seemingly comes from a legitimate internet address gives a researcher who's not so familiar with the command line a seemingly innocuous script that somewhere down the line has hidden some real problems. As luck would have it, Dockerizing the back end manages to make security at least slightly more of a sure thing. If the system were to be targeted by, let's say, some unsavory individuals, if it went bad, that is to say, if files within it got corrupted or if it got fork bombed, what would ultimately take the hit would be the lightweight container, which we could eliminate without too much of a problem, and then just spool up another one while we worked up why the security hole.
This is our Massachusetts Open Cloud OpenStack dashboard. Over here you can see a summary of all the resources we have used to implement CRIS. The instances, which are essentially the virtual operating systems, the CPUs, the RAM, the IPs, the volumes, and the storage. Under the Instances tab, we can in more detail see exactly what instances we have used to demo the functionality of CRIS. Both of these are Ubuntu images with floating IPs. The floating IPs allow us to SSH into these instances from a remote location and work on CRIS. These instances contain all the CRIS files which are necessary to power up the system and to make sure that everything works. This includes the Python plugins, the backend, the PHP frontend, and all the manifests and other files which are necessary to present the CRIS frontend and to interact with the backend. Under the Volumes tab, we can see all of the storage we have used to implement CRIS. These Docker plugins are about 8 to 10 gigabytes in volume each, and given the number of them, it was necessary to create additional storage to contain all of these plugins. Under Access and Security, we can see an overview of all the key value pairs, the floating IPs, and the accesses, which allow us to SSH into CRIS, to work with CRIS, and to make changes to CRIS from a remote location.
Trello is a workflow management tool that we use to record our progress throughout the semester. It promotes Scrum methodology, an agile software development framework that challenges old sequential approaches and encourages teams to develop a flexible strategy for reaching their goals. As you can see from our board, we neglected to use Trello to its full potential for the first 2 sprints. Our project similarly struggled during this time, but finally came together at the same time we began to use Trello more frequently. During the 3rd sprint, we learned to use Trello time estimates, although we did not accurately record time spent doing research for the project, and rather just time doing hard coding work. During this time, we learned how to launch the CRIS instance inside of VM onto the MOC, and spent the rest of our time installing Docker on the instance and trying to get all members of the team up and running. During the 4th sprint is really where we learned to use Trello to its full potential and recorded everything that was completed. We learned that Trello greatly increased our workflow, and because it provided an intuitive design to split our project into small chunks rather than a gargantuan task. During this sprint, we were able to get everyone to log on to the CRIS machine and mounted the file system and dependencies needed to run a plugin. Sprint 5 is where our team figured out how to run a plugin on our local machine using the MOC CRIS system. This meant that we had a working Docker file which would take input from the CRIS file system, convert it to a different format, and output it back to the correct location in the tree. We spent a lot of time with our mentor during these 2 weeks, and all understood the project much better. At the end of this sprint, all that was left to do was create the glue that held the front and back end together and allowed them to talk. During the last sprint, we spent a lot of time debugging the front end issues, and and figuring out how to spawn a Docker file from the local host instance. Once we figured this out, it was simple to copy the output correctly and Dockerize a few more plugins and stress test each. We also changed some of the plugin graphics to illustrate that they use Docker, and spent a significant amount of time creating this final video. As you can see, this is going to be our Sprint 6 burn down chart. We estimated that we would use approximately 75 hours and completed about 78. This is our burn down chart.
This project has been an excellent learning opportunity. First off, we learned about virtualization, creating VMs, establishing methods of remote login to these VMs, and building these VMs from base files. In the case of Chris, these base files were the GitHub repository with all the Python, PHP, and other files necessary to make Chris work. We then learned about the Massachusetts Open Cloud, creating and deleting instances, volumes, and networks. We learned how to manage instances and how to scale them as needed. In our case, this scaling was mostly related to disk space. We also learned how to access instances from remote locations and how to use the OpenStack interface. The majority of our learning came from Docker. We learned about containers versus virtual machines and how to build simple Docker applications. Using this knowledge, we applied it to build more complex Docker applications, more specifically the plugins in Chris. We learned about how to move data in and outside of Docker containers, and how to automate building Docker containers using Docker files, which are essentially scripts that automate the construction of a Docker container. Lastly, we learned quite a bit about the Agile and Scrum methodology. We learned about using sprints to accomplish goals. We also learned how to use Trello, and how Trello can be an extremely powerful tool in managing the time and tasks necessary to accomplish a project. We also learned about resource and team management. This was especially useful because in the real world, the classroom doesn't exist, so it's necessary for teams to work together to allocate time and resources effectively to accomplish goals.